Section 1.3, limits at infinity. So when we take a limit of a function at infinity, we're interested in the end behavior, what's going on at the end of the graph. And the way that we write that is exactly that we wrote limits before. Limit of f of x as x approaches infinity or negative infinity. Infinity would be this way, negative infinity would be that way. All right. So you should know what these look like generally, at least the end behavior, without a calculator. So we have a degree logarithmic function. Okay, and it's even for the third power is positive. So that means at the ends of the graph, okay, like we do something like this. But the ends of the graph are all we're concerned about. So as x approaches infinity, it's going upwards without bound. So the limit is infinity. Going the opposite way, it was heading down continuously. So it's approaching negative infinity. Okay, e to the negative x. You should know already that e to the x looks like this. And e to the negative x looks like this. So as x approaches infinity, this approaches 0. As x approaches negative infinity, however, it's going upwards without, so it's approaching infinity. Now, sine of x looks something like this. So as you approach infinity, it's not approaching one single number. It's kind of oscillating between negative 1 and 1. So it does not exist. And the reason why is because it's oscillating. It's going back and forth, up and down between negative 1 and 1 forever. Okay. Now we look at x times sine of x. The only thing that's going to happen is that it's going to get bigger oscillations. So that's not going to approach anything. It does not exist for the same reason as the last one. It's oscillating. Okay, but when we look at 1 over x times sine of x, as 1 over x gets, as you put big x values in, this is approaching 0. So even though sine of x oscillates, because we have that 1 over x, we're getting closer and closer and closer to 0. So the limit equals 0. Okay, so what we had just determined, any of these limits at infinity that approach a number, not infinity, okay, that's not a number, remember, that's just an idea. Any of these that approach a number, they have to have a horizontal asymptote at that number. So for example, part C has a horizontal asymptote at y equals 0, and part G has a horizontal asymptote at y equals 0. So here's your whiz question of the day. How many horizontal asymptotes can a function have? All right, we'll keep going. Now, arctan of x, this is something that you should remember what it looks like. If you don't, refer to a reference sheet or look it up online. It does have two horizontal asymptotes. So the limit as x approaches infinity of arctan of x. Okay, you put greater and greater numbers in. Y approaches negative pi over 2. So we have a horizontal asymptote at y equals pi over 2 and at y equals negative pi over 2. Example 3. A lot of times rational functions are but not always. In the first case here, the numerator has a lower power than the denominator. So that means the denominator is going to grow faster than the numerator. So if we put in a billion for x, we're going to have 3 billion squared over 5 billion cubed. The bottom is so much bigger that we can kind of lessen what's going to happen at the top. So as function gets bigger and bigger and bigger as the x values get bigger and bigger and bigger. F of x approach 0 because the denominator is growing so much faster. It's very similar to 1 over x. So if we put negative infinity squared over negative infinity cubed, either way, the cubed is still bigger, so it's 0. So we have a horizontal asymptote at y equals 0. Part B, this is a different case. The degree of the numerator matches the degree of the denominator. So they're growing at an equally fast rate. So this time, we're just looking at the highest powers here. The limit as x approaches infinity of g of x, we're going to have like 3 billion over 5 billion, okay? 3 quadrillion over 5 quadrillion. Either way, it's going to be approaching 3/5. We would be approaching negative 3 over negative 5, which is the same. So we have a horizontal asymptote at y equals 3/5. This is going to help us when we start graphing these functions. In part C, this time the numerator has a greater degree than the denominator. In this case, the denominator grows without bound, so we're not going to have any horizontal asymptote. So as we enter a very large positive number, it's going to grow without bound. As we enter a very large negative number, however, the top will be positive, the bottom will be negative. So we're going to be approaching negative infinity. So in this case, there are no horizontal asymptotes. However, because the degree of the numerator is exactly 1 greater than the degree of the denominator, it is going to have a slant asymptote, a linear asymptote. So it would kind of be a graph that would follow along a curve like this, rather than a horizontal line. And so that's what we're going to finish up with this last example, how to find a slant asymptote. So let's get this pen a little smaller so we can fit it all in here. So to find the equation of the horizontal asymptote, or all we're going to need to do is long division, which I'm sure you're all very familiar with. Okay, so we're going to have this 5x cubed plus 4x outside. 3x to the fourth is 0x cubed, 0x squared, minus 8x plus 12 on the inside. Okay, so now you have to figure out 5x cubed times what will give you 3x to the fourth. So the first part is just figuring out the x variable. That's easy because that's just x. But 5 times what? 5 times what equals 3? Well, you need something to cancel out the 5, and you need to put the 3 there. So we're going to have 3/5 x. If you multiply those, you'll get 3x to the fourth. So we have 3/5 x. I'm going to have to modify that by each of the terms. Okay, so 3/5 x times 5x to the third would be 3x to the fourth. Okay, 3/5 times x times 4x squared. It's going to give us 12x cubed over 5. Okay, now we're going to get negative 3/5 x squared. And so we get negative 6/5 x. So there's actually we're subtracting. So when you subtract, you change the sign. Don't forget that step. So we get negative 12/5 x cubed plus 3/5 x squared plus 6/5 and bring down to 12. 6/5 x. Okay. So now 5x cubed times what gives you negative 12/5 x cubed. So again, if you see that, this times something equals negative 12/5. replace that with okay, so we have negative 12 over 25 for the second part. Multiply that all out. Okay, so we get 12 over 5. Because when we multiply by 5, it cancels it out. X cubed. That would be, oops, 48. 48. Minus 12. 25x. And multiplied by the negative 2. We get minus 24 over 25. Alright, so using your brains, I'm sure you can do we get negative 33 exits. You gotta check this. over 25 x minus 276 over 25. And if you can remember, you do need to go back and change the signs. And I already kind of put them. So what this is saying is when we divide, we can't put it down because we have x squared and our lowest term here is x cubed. Okay, so what that's saying is this equation at the top. That is our slant substitute. Y equals 3 fifths x minus 12 25ths. Which is just the regular equation, so that would be easy to graph. Okay, so that concludes our first video for 1.3.